So I get the pleasure of introducing our next speaker, Napsia Buddhamatya. Napsia is a structures analysis engineer at JetZero, where she specializes in aeroelastic analysis to support structural sizing of the company's production aircraft. She holds a BS in both aerospace science and engineering and mechanical engineering from UC Davis, and recently earned her MS in mechanical and aerospace engineering from the same institution. Her graduate research focused on structural optimization and aeroelastic effects in blended wing body configurations, providing a strong foundation for her current analysis work. After 3 years at JetZero, she now works on the structures team to focus on advanced structural analysis, where she continues to apply her research and technical background to JetZero's next generation aircraft design. So without further ado.
Hi, my name is Napsia. It's Napsia. That's probably the only time I'm going to tell you how my name is pronounced because I'll be too shy to correct you later on. So, so it's Napsia. Thank you for having me and for all the people that came up and told me that they were excited to see this. I hope that you'll get a lot out of it, but not too much because I had to go through it 3 times to censor a lot of stuff. So in this presentation, I want to just give you a little summary before I start. I'm going to be talking about why flutter is so important for our JetZero aircraft and how HyperX fits into our sizing workflow, the results that come out of the workflow, and also the future development that we're hoping to continue working on to better the workflow and obtain better results. So I'll be talking about how we use HyperX and Nastran Sol 200 to do aeroelastic flutter sizing on the JetZero landed wing body. What's the importance of flutter on BWBs? So there's 2 major reasons. The first one is that the BWB generates like a different lift distribution compared to a traditional aircraft that's a tube and wing. So it creates more lift across the entire body. So there's less reliance on a traditional wing area. So that enables a more slender wing with integrated wing structures, which the slender wing can cause for thinner and less stiff structural components compared to the conventional designs. And so this non-traditional planform geometry alters the aeroelastic behavior a lot. And then the second reason is that the blended wing body, like our JetZero aircraft, is a pretty big aircraft. It's supposed to rival a 757, 767 size aircraft. So it's very big. And in order to reduce weight, we're going towards composite materials systems here, which overall kind of lower stiffness and in turn like the reduction of bending and torsional stiffness increases flutter susceptibility. So flutter is a big important part in our trade studies, and also like accurate flutter analysis is super essential to ensure structural integrity and flight safety. So just to go over the entire wing flutter sizing workflow, this workflow will explain kind of the entire workflow of the presentation, and just to give you a heads up, any of the boxes in blue will show when our FEM is in a pre-post processor like Nastran or HyperMesh, and then the green boxes will show you when the FEM is in HyperX. So first, we create a FEM with traditional FEM creation methods. We run our linear static analysis, perform VMT checks, and then move on to our first HyperX baseline wing sizing. So we bring the FEM into HyperX, apply our load analysis properties, run HyperFEA, and this will size our wing for strength and stability. After that, we bring it back into a pre-post processor and run for, It spoils. So we'll run it for flutter analysis. perform Sol 145 and see if it will pass our flutter requirement or not, and if it doesn't, we'll move on to step 4, which is trying to find a flutter optimized wing sizing. So it's mostly stiffness driven, so we try to find a method that can optimize the wing sizing for stiffness to pass the flutter requirement, and here for Sol 200, that's what we end up going with, and to do that, we modified our property cards, create our responses and constraints, and perform the Sol 200 optimization. And then lastly, with this step 4, you are optimizing for stiffness to pass your flutter requirement. So you will be losing the strength and stability sizing from step 2. So we have to put that back into step 5 and take the stiffnesses that we get and that we are aiming for and use a nifty tool with section cuts and stiffness constraints in order to resize the entire wing model for strength, stability, and stiffness. And then in this presentation, we're just gonna focus on these steps, these 4 steps, 2 through 5. So for step 2, to get the baseline wing sizing, we worked with Collier for quite a number of months, and in order to determine the weight optimized layout for our major wing substructures. So we studied these specific areas, and there were 2 major outcomes. So one, we had a better understanding of the substructure's sensitivity to spacing and chord location. And also, we were able to down select from the different configurations that we ran, down select a baseline wing layout for future studies, and then in this one we'll be talking about flutter analysis specifically. After the baseline wing sizing, we move on to step 3, which was our run a Sol 145 flutter analysis. So this flutter boundary graph shows a plot of altitude versus knots equivalent airspeed. So what we really want to focus on here is the red line all the way to the right of the graph. That is our 1.15 times diving speed boundary. And according to FAA, any aeroelastic flutter really needs to occur past this point, so on the right side. And looking at our initial sizing in purple, that's our flutter speed boundary. The initial sizing from our baseline wing did not pass the flutter requirement. So what can we do? We thought, what can we do to move this purple line past the red line, but right outside of it? So we move on to step 4, trying to optimize a wing for wing sizing for flutter. And so we tried 3 different trials in order to size the wing for flutter. So trial 1, we just increased the bending and torsional stiffness along the span to match a flutter-free sized wing that we had access to. We knew that this wing was flutter-free, and we tried to match our baseline wing to bending and torsional stiffness to that wing. And the second trial, instead of just increasing bending and torsional stiffness, we increased the GJ-EI stiffness ratio along the span to match that same wing. This was like a textbook method that we did. And then the last trial was coupling Sol 200 with HyperX to obtain unoptimized bending and torsional stiffness along the span, and then use that to also inform HyperX. So all of these, we will be using HyperX to resize for stiffness. So, and we relied heavily on the section cut definition tool. So in HyperX, you can open up your section cut definition tool, and we cut along the span in between each rib bay in order to get our section cut properties. So there's two important buttons that we used in this tool. The first button is the properties button. If you click that, you can get calculated properties. They use like common industry analytical methods to get these properties. So you click that button, it shows you, for this analysis, your two important property values here, EI and GJ. So these are what we're really focusing on. So we cut along the span and obtained EI, GJs in between each rib bay along the span to see what we're working with. And then the second important button in this tool is the constraints button here. In this menu, you can set minimum stiffness constraints for your bending and torsional stiffnesses. So if you know what your target stiffnesses are, you can input that there and resize in order to get a newly sized component with a minimum stiffness that you set. So let's see what we can do with this. So we use these two buttons. So we were able to plot bending and torsional stiffness along the span by obtaining the stiffnesses from the properties button for each cross section. And disclaimer, I'm just going to be showing what we did for SOL 200 with the two buttons, the properties and the constraints, but we did do the same process for every single trial. So with the cross-section tool, we got the property values, and we compared them between two different wings. So the first wing, our baseline wing, did not pass flutter requirement. It was sized for strength and stability. It's shown in gray. And then the other wing we're trying to compare it to is our SOL 200 flutter-optimized wing for stiffness. And so we can see past this point in the bending stiffness versus span graph, bending is dominant on the right side of this span location, and then for torsional stiffness graph, the torsional stiffness is dominant past that point. And so what we really want to do is be able to match the gray line to the yellow line, because we know that the gray line is already sized for strength and stability, but the yellow line is where the stiffness should be. So in come the resizing. So once we apply our targeted stiffness values in the constraint menu, we resized it, hyper-FEA, and we're able to get this orange original baseline adjusted line. So now this this orange line is sized for strength, stability, and stiffness. And you can see that here in the bending stiffness graph, there's a stiffness match in this area of the span, and then the torsional stiffness is also matching in that area. So let's see how that affected our flutter. So first we ran the first trial. The first trial, we adjust EI and GJ to match a flutter-free wing that we knew. So we just changed the constraint, resized it, and this is what we got. We got a flutter boundary that's way past our red line, which is good. It's not, we don't have any flutter, but it's really far out there, and we really want it to be closer, because it being out so far, we know it's like, oh, there's probably a necessary structure increasing our weight. We really want it closer to that red line. So we did our second trial, which is increasing GJ-EI ratios from our baseline wing to match our flutter-free wing. And we got this right here. It did not really pass the flutter requirement. It undershot quite a bit, and so we're like, okay, the first two methods, we just changed the stiffnesses, constrain them, and it was kind of a shot in the dark. Like, oh, we have this wing, we're going to try and match it. But we really need something that can give us a better stiffness estimate. So we have to rethink, like, oh, what should we do? So we ended up doing the SOL 200 method, and constrained the optimization sizing to pass the flutter requirement, and also maintaining the lowest weight. So we got the stiffnesses there, resized it for strength and stability in HyperX, and got a flutter speed boundary that is outside the red line within 7% of, within 7%. So how do all these trials compare? With the HyperX dashboard, it's very easy to compare them. We are able to look at how weight is distributed in the wing. And so here, our first original baseline, it had the lowest weight compared to all 4 configurations, which was expected. It was not sized for stiffness. It had a flutter issue. So for trial 1, remember they passed the flutter boundary, but it overshot it, and we expected it to have unnecessary weight, and so it did increase the weight significantly. But for trial 3, when we ran it with SOL 200 and resized it, it passed the flutter requirement, increased the weight, but not as much as trial 1. So we were able to reduce the weight and close that flutter boundary gap between the red line and the flutter boundary speed, the speed. And other than weights in the HyperX dashboard, we can also look at the controlling criterion. So the left shows the the weight, each component of the wing and its weight that is being controlled. And then the right shows the results from SOL 200. And comparing these two, there is a change in color. Obviously, the colors are kind of blocked out, the meanings of them, but there's a change in some of the colors, and specifically here, the purple and the yellow, there was a big increase in these colors after running SOL 200, so these were an increase in bending and membrane stiffness. So that shows that we did do something right to size it for, to get a sized wing that's flutter-free. So some key takeaways here. HyperX may not have innate aeroelastic capabilities, but it is extremely powerful and has tools available for supporting an aeroelastic analysis workflow. And so it allowed us to do rapid configuration resizing. We did 3 trials in maybe 2 weeks, and it's just like one engineer working at a time. So that's pretty impressive. But there's still continued development on it. Thanks to Bryce and other members on the Collier team, we are able to try to improve this workflow and this process using different automation, Python API and stuff. So we're trying to couple SOL 200 with HyperX in order to make the whole process more iterative. Because currently, from what you've seen earlier, we only did 1 pass from SOL 200 to HyperX for resizing. But if we use these, the HyperX result post the first SOL 200 run as a seed in order to loop through SOL 200 again and then resize it again, we will hopefully eventually converge to a more global minimum in lightest weight, and then it all will be sized for strength, stability, and stiffness. And to kind of show you what I mean by this, we can take a look back at our graphs from before. So on the left, first let's just focus on the left graph. Kind of ignore the red text and red arrows. It's a little confusing, and I think it doesn't make much sense. But ignore the red text and red arrow, and focus on the orange line. So after resizing and getting the adjusted baseline in orange, we can see that in the middle, I don't know if you can see my laser. In the middle right here, there is, shows that there's more, there is an increase in bending stiffness that's more than the original baseline and also more than the target Sol 200 optimized that we wanted to match. So there's like a lot of room here to reduce stiffness, unnecessary stiffness, and also reduce weight. So if we ran it through Sol 200 and HyperX again, maybe we can reduce this gap here and also close the gap in the flutter boundary there, and bring that VF boundary closer to the red line. Thank you.
Hey, Napsia, great presentation. My question for you is, when you were defining your EIGJs, did you have to define an elastic axis, or were you able to let HyperX determine that on its own? Because I saw you had centroid up there when you go back up to the charts. I know most time when we do aeroelastic analysis, we choose an elastic axis that we reference around.
Yeah, I think we did. Yes.
Okay.
And I'm gonna deflect that to Logan because it was so long ago. We did the section cuts, and then we did define a different coordinate system.
Yeah, we let HyperX determine the principal axes that we were for the EIHH. That's your horizontal axis, right? That was just what HyperX calculated from the cross section. Yeah, is that what you're talking about?
Yeah, and normally you want it set when you do all the trades. So if you let it determine it when you updated sizing, did it move? That would be my question.
I can maybe answer that. So you can define the origin on the section cut and like leave that constant and define all the properties about that origin of the cross section. The CQ will move depending on the sizing results.
Okay, yeah, that answers the question. You kept it constant then.
Yeah. Quick question. So I saw that on the form you had the slider in the middle, pretty much. Did you play around with that to try to reduce the weight while still achieving the stiffness requirements?
Sorry, which one?
If you go back to the form, the section cut form, the constraint form. Yeah. So I was wondering, that slider that under the zone stiffness distribution heading, did you just keep that fixed, or did you slide that around so that you could still achieve the bending and torsional requirements while lowering the weight, like sliding more towards the right?
No, we kept it fixed.
Okay, that's something that you can play around with, okay. Improve your weight.
Okay, thank you.
Out of curiosity, when you were covering your flutter, do you know what mode you were getting as your most critical? Torsional, body flutter?
Yeah, so with here, we saw that the torsion was more critical, according to this graph.
Great talk, Napsia. For the interaction between Sol 200 and HyperX, is this something you're doing with it with a Python API, or something that you're still managing with manual iteration? Just curious.
With Sol 200 and HyperX, we did that manually.
Okay.
Right, for this workflow.
Is that something you want to, automate later, or?
Yes. So we got some help from the Collier team with some automation codes and scripts. So we're going to try to automate that.
Sounds good.
Thank you.